Swayam Prabha. Digital India. Educated India.
So the first software package or commercial package I have been using, and also here you can see is a mic DHI software. And from last couple of days communication with you all, I realized some of you are also using DHI model. It's quite user-friendly, I believe, yeah, and also easy to learn. But also it's very challenging if you are trying to use that very well. Yeah. So here, for DHI model, there are different modules. But when we are coming to the wave model, we use Mic 21, yeah, SW, the spectrum wave model. So these are different modules we have been able to use. So I use Mic 21 and Mic 3, but for Mic 21, for wave model and also for flooding model we have been using. Mic 3 I use a lot for the Bay Area and the lake and also the reservoir, yeah. So for the Mic 3. And also for the Mic 21, there is a boosnistic waves. That one, if you are doing some structure design, that can be used if you are doing that. Then of course, what else I have been used? Okay, I did use looking that for the sedimentation transport, but that can be included in that. So actually for the Mic 21, also there are shoreline morphology, but I haven't used that one. We use Ecolab. That's what we used, Ecolab. So, of course, that all depends on the need of your project, of your study, the problem of your investigation. So, for the Mic 21 Spectrum SW module, that's really powerful. So you are able to use that for the different applications. We mentioned before, like offshore energy, coastal structure, infrastructure, and also if you are doing the coastal resilience. That's nowadays we also do a lot, because when you are talking about the resilience, you are talking about the risk or damage, then a lot of time have to be based on the wave data you are having. Otherwise, you won't. Port planning and design, of course, environmental impact. So all of that are able to use a Mic SW modeling result and then continue what you are doing. So there is an example you are able to read. Actually, that's published by DHI. It's a Port Brisbane study. So I always use that as a good example for the student to look at what can the DHI model be used for. So that's just for cost and efficient planning. And so that's very quickly what is a spectrum wave. Remember, we introduced the spectrum analysis, and also you are able to see the distribution of the waves, for any waves. And when you are using the spectrum wave, basically the core part of that is this equation. It's the energy, right? So everything is based on the energy. It's a balance of the energy. So you got from the wind to generate the energy, and then you have the all the different energy loss. Can be from the braking, can be from the white capping, bottom friction, but everything has to be balanced. So that's a key equation. And also there are the partial differential part. So you have the time domain, and also you have all those what's the spatial domain, and also you have lots of the boundary conditions input. So although there is only one equation listed here, but a lot of the parameters and the variables, they are interact to each other, depend to each other. So it's not just a one single equation. This is one of the case. We have been set up the model. So this is a Gold Coast area. So that's a Gold Coast area. We have all those like the buoy or measurement point, like we list here. So those are the we list all of those measurement points, either for buoy or for those like a profile transact. And we set up the boundary for this model. So that's what we set up, okay? Because that's covered the area of our interest. So all those beaches, all those key beaches. And also because we have the bathymetry information, we have the wind data, that's what we used. And what we did for this one, actually we did have a mesh sensitivity study or convergency study. Try to find the most efficient mesh. Not too fine, not too coarse. So that's what we did. So we have been doing that. And
what is the size of grid?
Sorry?
Size of grid.
The grid?
Grid size.
Oh, I can't remember exactly the. It's a flexible.
Flexible.
Yeah, it's a flexible mesh. It's not a grid. We use it's a mesh for this one. I can't remember what's the smallest we have, but in the publication of our paper, it should have all those informations. Yeah. But you are able to see we have the gradually change from the offshore all the way to the near shore, the different dimension. So it's varying. And when we are making all those selections, actually we did plot out a 2D comparison. And we realized that, of course, in the coastal line area, we have to have a finer mesh. The discrepancy is larger. So then we have to get a finer mesh near the coastal area. That's what we are having. So you are able to see the coastal area, the mesh are finer. So that's our finer mesh. So all of that based on also the shape we follow is basically the bathymetry contour lines a lot. Yeah. Another thing we look at is boundary condition, but this boundary condition actually is for the wind. So what type of a wind condition we are using? Because if we use a local measurement of the wind, then we don't have very spatially distributed. We only have a couple of the monitoring stations. And then we also have analyze the wind condition. So we try to looking into different wind condition for that. That's for the wind. But also at the boundaries, we are having that. We also use a few different ones. So one is a wave watch 3 output, and another one is the ERA5. So we did have a different comparison of all of those informations. Try to get the best. So we have the comparison. And basically, we have the near shore wave watch 3 result. We found that will be the best agree with our monitoring information. So that's a kind of the calibration or a kind of the validation of the boundary condition you are able to use. So a lot of informations we need to do that. And when we come to the calibration of the wave result, we also have to, if you have done that, you know there are many parameters you are able to do that. Break index, wet capping coefficient, or bottom friction, the sediment size for the bottom. So all of those parameters you are able to do the tuning and then try to get the best fit. But the problem we are facing is sometimes when you think, okay, this is the best fit for this calibration period, but when you are using this result for a validation, another period for the validation, but then the discrepancy is not good. Or sometimes when coming to you get the best fit for a storm time, but then for the normal time period, then the agreement will be not that good. So that's the things we always try to work on and try to get the best for your project. So if you are concerning more about the storm season, then your focus will be on the storm season more. And also, another thing is, I think I didn't mention in these slides, we also try to use AI to do the error predictions. So based on the existing result and also the monitoring, there is an error between the measurements, and then we try to predict the error for the future. Then you can add that back to adjust your final outcome. So we also add on that part in the model as well, but that's not in the model. It's the post process of the information. So when we are looking at the result, not only looking at the wave height, so we also look at the energy distribution. So that's the polar graph we used as well. So you are able to see, for example, the waves, the spectrum distribution, what range of the direction, and also what is the range of the period. So this type of the diagram from the DHI model, you are able to extract all those informations. So this is just an example for the southerly storm. That's the ABC. So this is a southerly storm for the first one. And then we have the northerly. But that's for the storm, what the energy we are able to extract, you are able to get. So once we get all those results from the DHI model, the SW file, then we will apply that to our beach profile analysis. So we got those transacts. So we just use a tool in the study for that. So one is here and one is here. And this is for one of the example, what is the original profile is to look like. Then so then we have this one. We look at the joint probability analysis. We include one is a significant wave height and the storm surge. So we include both. And before we are applying that, we did, based on the available significant wave height measurements and the storm surge, then we find out, okay, what are the cases we think we need to look at more. So one is a low significant height, but is a high storm surge, and average, and high and low. So we had those cases for our analysis. So this is an example when we are doing the storm surge and wave height. We also did the extreme, the peak over threshold. That's what we mentioned before. So we did for both of that. So that's a threshold value, and then we use a GP distribution. So to analyze all those over threshold data set. We get the value. And then is for the storm surge, we use the same techniques. Okay, that's above 0.28, I think. That's extreme value. Again, we get all those like extreme surge. Then we find out all of this data, the dark point. So that's all the dots. That's from all the information we have. But we did the joint probability. We use this part of the data for the further analysis. So that's the techniques we used. And then we use X-speech models so to do the predictions of the beach profile change. So that's just a few examples. You are able to see the dark lines, that's an equilibrium profile. And this few, the dashed line, the short dashed dot line and dashed line, they are all, one is a measurement, and which one is measurement? Yeah, this is a measurement. The dashed line is a measurement, and the simulated is a dotted line. So you are able to see they are in a very reasonable good agreement. So for quite a few storms, so we did that. So they all did a reasonable good result. So that's one of the application we use. And also what we are able to use this one is in the future, if we expect a certain storm are coming, then we are able to know what will be the erosion or what will be the profile change. So we did quite a lot of the analysis on that. So this is one of the example we have. And then another example here, we also use a DHI model, but this one we use a DHI Mike River. That's before it's a Mike 11, now it's a Mike River, and also the Mike 3. So we integrate those two. This is in Australia, in Queensland again. So you can see these lines over here. That's the Brisbane River. So that's the largest river in southeast Queensland, and this area is Moreton Bay. So all the river will be discharged over to the Bay Area, and the port of Brisbane and the airport, they are all near the river mouth. So the sedimentation, yeah, everything will be coming to this area. And at least in this diagram over here, that's another area is Wivenhoe Dam. So I will not talk about it here, but this will be the main discharge from this dam to the Brisbane River. So if there are any storm or flooding event, the dam will be released. The water will be coming to the Brisbane River. So that's this side, and that's Bay Area. So this is a Brisbane River estuary catchment and the estuaries. So that's one of the big catchment. 2011, there is a big event. So this is one of the largest event in last 50 years. So you are able to see the whole river band over here is just like everything is like a yellow, very yellowish, so a very high sediment concentration. So in the Brisbane River catchment, and the water level is also very high. And at that time, a lot of property has been flooded in the city area, and even in, I think, University of Queensland is just near the river bend. Some part of the campus has been flooded as well. So that's a big one. But what's our concern over here when we are looking at that? That's a sedimentation is one big thing during the event, during the flooding, not only the inundation, but also the water quality as well. So both quantity and the quality. So that's what we are looking into. So we did a comprehensive study in that area, and we tried to not only set up the model, but at the same time, we also use a lot of different measurements techniques as well. Because for the modeling part, you know, for any model, you won't get exact description of the equation. And a lot of parameters, they are like simplified to like a kind of a linear or constant or so, but that's, we need to also further investigate that. So based on this type of the situation, what we have done, first we did the river part. So you can see the change. So this will be the tidal limit, so which means the intrusion, the seawater intrusion will be not passing over this area. So that's our tidal limit. And this is a river mouth. So the change is roughly 85 kilometers in the total length. And in Australia, we have very good data sharing. So we are able to assess a lot of national department or state government. They have a continuous monitoring along this river. So on all of those green points, we have the monitoring data. So we did looking back like a historical data and see what is the condition over there. So you can see that we have over 20 years information. And what's in this river, so the bathymetry is varying a lot, but the mean tidal range actually is like this. For the neap tide, 1 meter, but for spring tide is 1.8 meter, is larger. And the depth of the water is between 4 to 15 meters. So that's roughly what the condition over there. So as I mentioned that we got a lot of the information. So we look at, because our focus was on the 2011 flooding. So we look at the seasonal variation in this area. So what's the discharge rate over here? So in Australia, the season a little bit opposite. So that's our winter season, relatively dry. And this is our summer. We have more storms. So we have a relatively higher discharge rate during that period. And what we are able to see, the salinity, because the saltwater intrusion over here, then we are able to see, okay, what's a range variation for different months, and alone this is a change. So what do they look like? So this is a distant from the river mouth. We cannot say that's change. So this is a river mouth, and this is a tidal limit. So from the tidal limit, you know the salinity is relatively small, right? Because the salt water will not be able to reach there. So one is a wet season, one is a dry season. So we do, no matter what catchment you are doing the study or what domain, we always look what's the condition in there. Then it helps you to decide what to study, what are the parameters. So by using the Mike model, we are able to get the analysis as well. Not only the measurements data, we are able to get the vertical profile of all those parameters you are looking. So if we're looking at that. Oops. So the salinity vertical profile, so you are able to see that. You can see in some period you get stratified, and in some period you got well mixed. So that's from the data set you are able to see very clearly in summertime. is stratified. In winter time, that's more well mixed. So all of those information gives you the idea about the structure of the water property in the river. Again, this diagram also showed you the peak turbidity in the river channel as well. So gives you, that's again, this is a change or the distance from the river mouth, and this is the turbidity. So we are able to see, no matter what season, actually, that will be the area you always get the highest turbidity. So that's in the wet season. And in dry season, that peak turbidity area or the peak turbidity zone relatively not that obvious, but still concentrated in this area. So that's for the estuaries, always have this. So it depends on the ratio between the tidal flow and also the discharge from the upstream. But that is where we are able to identify these locations. So again, that will be the colored, the data set you are able to see, the turbidity distribution. So we are able to see all different distributions you want to look at. Different period. So this is in the wet season, February, our summer season. Normally we get a large flow coming from the rainfall. And also the runoff in the Brisbane River with the sedimentation is always very high. We have a very strong correlation between the discharge rate and the sediment concentration. So I'm not sure here, do you have the similar type of the phenomenon or not? But for us, we have a lot of the sediment washed to the river in the rainfall period. And then in the winter time, you will see higher concentration near the riverbed because that has a more settlement under the water with a less flow coming. So that's what we are having in the Brisbane River. So this is we first look at. But when we are trying to do the modeling, we need to have the concentration very clearly, or as a boundary condition to the Bay Area. But normally during the flood period, we don't have the measurements. So a lot of one of the big reasons is safety. So we don't do the measurements during those high water level and the storm season. So the data is missing. But now a lot of available satellite information. So that's, we tried to extract the satellite information and to correlate that with the concentration. So that's what we have done. So we extract those information and then get the existing measurement data. Then we get some data-driven type of a model. Then later, we did use this model to generate the concentration of the sediment and use that as the output, as the input to the Bay Area modeling. So that's what we include in the model for our boundary. So that's for this one. And then we have field experiment. We got a research vessel, so also we found out for the sedimentation transport or for the salinity, for those transport, the dispersion coefficient is always, we just assume it's a constant, but that will affect the transportation of the the substance of your interest, no matter it's a sedimentation or is what we call, or is a salinity or some pollutant. So then we did experiment. We tried to get the two type of drifters. So one is we call that a smaller one, a smaller drifter, and another one is a self-located data marker buoy. So those two type of the drifters we used. And then we select a location. So those marked in red. So this one, that's in open water. So you can see that's in the middle of the bay. And then we select another one is like a between island. That's this one. And then we have another one is a near shore. So we are trying to see what the dispersion coefficient will be changing in this different area. Before we just constant in the whole domain. So now we are designing the experiment for that. Then we throw the drifters in those areas and then to track. Because each of the drifters will have their GPS, so we are able to track. And when we are throwing those drifters, actually it's a cluster. So it's not just a single one, it's a group. So there is a cluster of that. And then we throw that in. Normally we did is 12 hours, one tidal cycle. Then we try to get back and then analyze this information. So from that, so you can see this example, that's between the island. That's the case. So we followed that result, and then we did our simulation as well by using this one. So of course you can see that's for the 4 drifters. Then we did the analysis, and then we tried to get the relative dispersion coefficient for the area. Then we will use those parameters back to our model. Now we are not using the constant. Then we are using a varying coefficient in the models. So we input that to the model. This is between the island. And then this one is in the open water. Again, we also using the varied, like relative dispersion coefficient, not a constant anymore, and then implement that to our model. So that's from the monitoring result. So then we look at the dispersion coefficient. We're looking at the dispersion coefficient from our simulation and also our measurements. And then we have those like pre-studies. One is a sedimentation concentration. We use remote sensing as an input. And then we have improved dispersion coefficient. Now we will come to look at our DHI Mach 3 model with sedimentation. And this is a model we set up. And also, you see there are lots of marks over there. All those marks, like the labeled number, that's where we got the measurements. So you can see in this Bay Area, there are quite a lot of measurement and monitoring stations, so which gives us a confidence about our simulation. What else? Yeah, so that's bathymetry files. And the water level you can see is up to 35 meters. And for this model, we are including not only the Bay Area, so we include the Bay and also the river as well. So we have both. We integrate the Mike River and the Mike 3 for the study. Here are some result we are having. So for the result we are having over here, this is a flooding event. For this flooding event, initially, so you can see the 1st of January, you start to have the flow coming. So that's before the flood. And then gradually, what's the color? I didn't show the color over here. So the color is the sedimentation concentration. So it's a sedimentation concentration. Then gradually built up, then you are able to see the built up. So that's the model is able to get all of that extraction. And I want to see is this one. So we had some comparison with the modeling result over here, and then again compare with the satellite image. This is just an area to comparison to see how big the area has been affected by the sedimentation coverage. So that's what we are able to do to validate the model as well, how trustful the model we are able to use. For the satellite information is sometimes if there is a cloud coverage, then we won't be able to get that clear information. But it is still we are able to use that as a reference to do our comparison or validation. Any question? So we are not only looking at the surface. So the beauty of the 3D model, then we are able to see all those different transects, right? Horizontal layers. So this one gives you the horizontal layer for the each of that, the slice. You are able to see. And also you are able to see the vertical slice, So then we are able to see how the vertical or horizontal and the plume has been evolved. So that's very clearly we are able to see. And also we did derive formulas actually to quantify the discharge rate and also the tidal power. What's their relationship between each other and what kind of plume will be formed over there. So that's all based on our simulation data. Then we are able to get what we are having for the next part. And here, this is just a 3D simulation, not 3D, just animation. So this is showing the river discharge for this whole event. And this is for the sedimentation, the sea surface concentration of the sediment. How does that compare to this storm? So that's at the peak. Now it's close to the peak, yeah? And then so the flood event has been finished. So that's for that flood event. That's in a couple of days. But when you are keep simulation, when those sediment will be flushed out, it takes a very, very long time. So for us, our simulation show that at least 2 months for this sediment will be flushed out. But the reason we concern this a lot is because up the north over here, if we go in further up, then that will be the Great Barrier Reef area. So the sedimentation, how does that impact to the Great Barrier Reef is also our concern as well. And this result can be used for the upper Great Barrier Reef area studies. So that's what we are having. So for the plume. So that's at least 2 months. So this is one of the Mike 3 model we used. Then we look at a next example. And here we did another example. This is in the Logan catchment. So that's in the Logan catchment. This whole area. So it's in the Moreton Bay. That's before we are having. So this here is in the bottom Moreton Bay, and then in this catchment. And Logan catchment compared to Brisbane, Brisbane is a more developed region. Logan is underdevelopment because the population in the Brisbane is higher. So the city, the planning, the next stage is in Logan. But for the Logan catchment, originally they have a couple of the wastewater treatment plants developed along the river. So after the treated water will be emitted to the Logan River. So it has potential of some water pollution issues. So we try to investigate when to release the treated water, because we don't want to, when it's in the high tide, to push on, then all the emitted water will be pushed upstreams. So we would like to, like in the low tide period, then this will be diluted and washed away to the Bay Area. So, and how and when and what kind of the potential risk in this area. So we all want to do that. So that's initially is because of this. But later, also there are flooding events happening over there. So we also try to look at because we are developing this area, we would like to know where we are able to develop those residential houses. We don't want to build those properties on the high risk of flooding. So that's where we start to look at. So again, when we are looking at all of that, we have to identify what are the issues, what are the data you needed. Like any project, you also have these type of things. And because we want to do the future planning, then what we need to know, what is a future land use, right? That's one thing. And what is a future climate. So I believe you all do a lot of the climate change activity as well. So before we are doing that, we also do trend analysis. That's when you are looking at the historic data. That's very important. And then extreme event, of course. Identify what are those key or principal factors. So that's we are looking into. So for the first part, we did all of those analyses. Then we try to set up the model. So for any catchment study, we need to have a good hydrological model before we do hydrodynamic. And for the DHI model, it has, I think it's a NAM embedded in the DHI model. Yeah. Yeah. So we can use those built-in hydrological model in DHI. But we also use the SWOT. Yeah, we also include the SWOT. SWOT. Yeah, yeah, for the hydrological modeling. Yeah. So for that one, we are able to include not only the hydrology, but also the water quality as well. Yeah. So we also include. For that one, the calibration is always very time-consuming and also very challenging. But we try to get all of that because you can also include the groundwater part in, so a lot of different, and you are able to include in. So we did have that, and then coupled this with our DHI model. So this time we use Mike River and Mike Flood. And then, of course, include the Ecolab for the water quality part. But when we are doing all of that, so it's really important to do the uncertainty analysis, because when you are integrate all those models together, then the uncertainty from the upstream, how that affects the downstream models. So some model is sensitive for certain parameters, and some model is not sensitive to that parameters. So we are trying to do all of that. And at the same time, we did all those like performance for each model. Again, we have to have a very, apart from those advection and the dispersion parameters, we also try to identify the pollution source and also some erosions, if that identified in this channel. Because we are working this very closely with, we call it SAC Water, which is a water utility in our state. So they are looking after the infrastructure or the asset of this catchment. So they said, okay, there are the riverbank erosion and is a big concern. So all of that we have to add into the model and to do the assessment as well. So that's modeling part. So now first we have the data analysis, then we have the numerical model part. Then the next one, actually, monitoring. Monitoring is also another important part. So for the water quantity, is a relatively like well organized and also monitored. But for the water quality, so in previous years, we always have is water sampling to get the water quality parameter, and then took the sample back to the laboratory, do the analysis. And so that is a very sparse data. But for some parameter, you are able to use probes, a sensor, for example, the turbidity or the fluorometer, so that you are able to measure the F-dome, so all of that. But still, for some parameters, we don't have the good measurements. So again, now what we are doing, one thing is try to use those like new sensors. So we have one is an eco detection company. They developed a autonomous sensor unit. We are able to deploy that in a certain location. But for that one, because it's very expensive, we cannot have that in many different locations. So you can only put that in some key or hotspot location. So that's what we are doing. So it's advanced sensor technology to be used. And another one will be the remote sensing data again. So we are also using the remote sensing data and try to correlate with the relationship with, if particularly for the lakes or that one, we use chlorophyll A. What's the correlation between that from the coloring and from that to identify any issues. So satellite image. So we use a drone to fly and with some high resolution camera also used. So all those different type of techniques we are trying to use to help us, not only monitoring the quality of the water, but again, then we're back to that also help us to validate the model. Yeah. So that's the whole project, what we are trying to do. So of course, if all this has been done, the model already set up and calibrated, validated. So is your job done? Yes or no, right? Yes, the first stage is done. Now you got this tool is ready, then we are going to do the next part. That will be your manager, your government. They are going to make decision. They are going to use this big tool you developed to do help them to make decision. So what decision we want to make? One is climate change. So the sea level rise, the rainfall pattern change, temperature increase, all those different like climate indicator. How does that? We are able to put all those scenarios, right? Drive your model to get the outcome because your model is trusted, is reliable. Then we find the rainfall pattern and all of that. So that's one. And then, of course, extreme. So in Australia, we have extreme storm, but also we have a drought. Yeah. So not only the extreme high is a high risk. Actually, the drought is another big risk as well. Not only like you don't have the sufficient water to drink. At the same time, the water quality will be a big concern as well when the water level is too low. So when we are talking about extreme, that's low and high. Of course, then the land use. So more residential house or more urban development, or this land is still kept for the agriculture. So all of that different usage of the land will have different impact to the model. And of course, not to the model, it's to the our real catchment. Mm-hmm. So that's another circumstance. So all of that, then we will be also coming to how we manage the wastewater treatment plant. So that's a wastewater treatment plant. How are we going to manage our dam? Mm-hmm. How to control the erosion. So all of that will also again affect your model input. Then after this all can be done, of course, then you will get the last part is a decision. So then that will be a big decision. So this is the whole thing, not only for my project. I think this same thing can apply to your project, everyone's project. So when we are doing that, the vision will be like that.